Section 7.3 is on logarithms and logarithmic functions. The inverse of an exponential function, that is y equals b to the x, is x equals b to the y. Notice and remember that the inverse switches the x and the y. But there's no way to solve this equation, x equals b to the y, to solve it for y. So we use logarithms. Y is the logarithm base b of x. In other words, this is how we deal with solving this for x. Or I'm sorry, for solving this for y. So if b to the y equals x, if that's the exponential form, then we can say that's equivalent to log base b of x equals y, and this is logarithmic form. Notice that the base in the log, the base is a b, or it's going to be a number. It's written as a subscript, and if we take that base and we raise it to the power of whatever's over here on the right side of the equal sign, it equals the large number right here. So log base b of x equals y means b to the y equals x. And it's a little formula that's probably just best to memorize. Let's take a look at a couple examples here. So we need to write log base 4 of 16 equals 2 in exponential form. So remember, this 4 is a subscript, so that's our base. The number to the right of the equal sign is my exponent, and it equals the large number that follows log. So log base 4 of 16 equals 2 means exactly the same thing as 4 to the 2 equals 16. Now let's try going the other way. We need to take something that's in an exponential form, that is 125 raised to the 1/3 power equals 5 in logarithmic form. So I'm going to write this as log base 125, because that's my base, of 5 equals 1/3. That means with the base of 125 raised to the 1/3 power equals 5. Now we can use this to help us evaluate logs. So we need to find what is log base 1/2 of 256. What that means is 1/2 raised to some power equals 256. So 1/2 raised to an unknown power, which I'll call x, equals 256. And as we saw in the last section, we can solve this by rewriting these two expressions with a common base. I'm going to use a base of 2, so 1/2 is 2 to the negative 1 raised to the power of x equals, oh, sorry about that, 256 is the same as 2 to the 8th. Okay, let's simplify this and get rid of the parentheses. 2 to the negative x, because negative 1 times x is negative x, equals 2 to the 8th. And now that I have the same base, I can just pull off the exponents and make them equal. And solving for x, x equals negative 8. So what that means is that log base 1/2 of 256 is equal to negative 8, or 1/2 raised to the negative 8 power equals 256. So as we did with exponential functions, we can also graph a logarithmic function. And that's going to look like f of x equals log base b of x, where b is not equal to 1. So in other words, your base cannot be equal to 1, because 1 raised to any power is always going to be 1. Our domain for this function is x is greater than 0, and our range is all real numbers. And in this case, my y-axis is going to be the asymptote. Recall from an exponential function, the x-axis was an asymptote. And in this case, I don't have a y-axis, since it's an asymptote. I have an x-intercept. My x-intercept is 1, 0. So if my base is greater than 1, my graph is going to look something like this. Okay, and it's going to be going down, and as x approaches 0, y approaches negative infinity, and then it's going to continue to grow, kind of looks like exponentially as x approaches infinity. If b is a number between 0 and 1, then as x approaches 0, y approaches positive infinity, and as x approaches positive infinity, y approaches negative infinity. And notice I have very similar points as on my exponential function that take into account what b is. Basically 1 over b comma negative 1, 1 comma 0, my x-intercept, b comma 1, and similar points for this graph right here. So let's take a look at a couple basic examples. Here I have the function f of x equals log base 2 of x. So in this case my base is 2. So from the previous graph that had the b's and the 1 over b's in it, I can make a table of values here where I have 1 over b, so that's going to be 1/2, comma -1. And then I have my x-intercept of 1, comma 0. And then I have the point b, comma 1. So let's go ahead and graph those. So 1/2, -1, 1, 0, and 2, 1. And I know it's going to go down like this, and the y-axis is an asymptote in that direction, and it's going to continue to move out that way. Don't be too worried about a whole lot of points. If you can get those three, that's really helpful. Okay, let's take a look at an example where my base is a number between 0 and 1. Here's log base 1/3 of x, so my b is 1/3. And again, I'll make a simple table with those 3 points. So I'll have it's easy to put the x-intercept in. And then my first point is going to be b over 1, or 1/3. I'm sorry, b comma 1. So negative, or 1/3 comma 1. Then my x-intercept, and then 1 over b, which is going to give me 3 comma -1. And let's graph those points. So 1/3, don't worry about being super precise, just kind of get the idea of where it's going to be. And then 1 comma 0 and 3 comma -1. Again, my y-axis is an asymptote, but in this case the graph's going to be going up, and in this direction the graph kind of goes out. And as we've seen with other functions that we've graphed, especially the exponential function, we can do transformations on this logarithmic function as well. So the basic function is log base b of x, but I can do transformations that would look like f of x equals a times log base b of x minus h plus k. And you'll see that h and k just keep coming up. So if h is greater than 0, my parent function is going to shift to the right. If h is less than 0, it's going to shift to the left. A positive k shifts it up, and a negative k shifts it down. If a is less than 0, so if a is a negative number, my whole graph is going to be flipped over the x-axis. If the absolute value of a is greater than 1, so in other words, any number greater than 1, it's going to be a vertical stretch. And if absolute value of a is between 0 and 1, it's going to be a vertical compression. Now, let's take a look at an example here, and it's a little more challenging than when we graphed exponential functions because I really don't know how to put this into the calculator. And the problem is that this one here is a log with a base of 1/6. It's a little problematic, so we're just going to have to kind of do our best. So we have f of x equals -1/3 times log base 1/6 of x plus 2 minus 5. So remember that my parent function is going to be, let me not use an equal sign, the parent function of this is going to be f of x equals log base 1/6 x. Okay, so if I were to take away like my a and my h and my k, that's what I would get. Okay, so I think the first thing I want to do is let's go ahead and graph the parent function. Oh, maybe I'll just go ahead and graph it in black. So the parent function is going to give me the points 1/6, 1, okay, 1, 0, and 6, -1. Let's see, 2, 4, 6, -1. So that's what my parent function looks like. And maybe I'll just go ahead and write it here. So this is f of x equals log 1/6 of x. 1/6, log base 1/6 of x. Okay, now let's go back to what we have to graph, and I'm noticing a couple things. I notice that a is equal to a -1/3. That tells me a couple things. It's going to be flipped over the x-axis. And because it's a fraction, it's a number between 0 and 1, it's going to be compressed vertically. Okay, and I notice that my h is -2. Remember, it's x minus h, so that means I'm going to be shifted left 2. And my k is -5. That means I'm going to be shifted down 5. So since I can't put this in my calculator and get a table of values, I'm going to have to actually do actually do the transformations here. So the first thing I'd like to do is flip this over the x-axis. So in other words, every point on this parent function that I graphed here needs to be transferred to the same spot on the x-axis. Whoops. Okay, so this point here goes right here. That point stays the same since it's on the x-axis, and this point here goes up to here. So this graph here represents a flip it over the x-axis. Compressing it vertically, that's just a little too hard to do. I'm not going to worry about that right now. Now I'm going to take this and I'm going to shift this one that I just flipped, and I'm going to move it to the left 2 and down 5. And this is going to give me pretty close to my final graph. So for this point right here, I'm going to go left 2 and down 5. 1, 2, 3, 4, 5. Okay, so that was this point here. This point here, left 2, down 5. And then this point here, left 2 and down 5. Let's see. Hold on. 1, 2, 3, 4, 5. Okay, there we go. So my final graph is going to look something like this, and it is asymptotic to the line x equals -2. So these graphs are a little more difficult. I'm not looking for precision, but it's a really great idea if you can show me what the parent function is and then what are the transformations that you're actually doing. As long as it looks pretty close, I think I'll be okay with that. So in this section, we took a look at logarithms, what a logarithm is, what graphs of logarithmic functions look like, and we looked at how to switch something from exponential form to logarithmic form.